And now I would hand over to Zeynep to introduce our final invited speaker.
Thank you very much. It's very nice to see everyone here, and it was a very exciting session already. Now the last talk of the session is going to be given by Gita Kutyniok. She is the Bavarian AI Chair for Mathematical Foundations of AI, and she is also co-director of Konrad Zuse School of Reliable AI, also known as RELAI. Her research focuses on mathematical understanding of AI and also using AI to understand mathematics, to improve, maybe. We are very excited that Gita is with us today, and I would like to call her to the stage. Thank you.
Yeah, thanks a lot for the very nice introduction. Also, thanks to the organizers very much for the invitation, for having me. I think we live in really exciting times because what we see these days is that AI becomes already part of the scientific infrastructure, and during the next years it will go even further. If you think of agentic AI, AI will become a close collaborator of us. It will be able to do many research tasks also autonomously. And so this raises then the question, what do we then expect of AI, of such a part of scientific infrastructure? Sure, it should satisfy the same standards which we require of every scientific instrument. And if I would ask you, I think questions like, can we trust it? So reliability would come to our mind, and maybe also sustainability. And so these are the two aspects I would like to discuss today. It was already said, I'm coming more from the foundational side, but we will see that both will also have to do with actually the hardware we compute on. So we need to also dig deeper than just the software layer, and we will see that also there's a tremendous impact. So let's start with a bit high-level viewpoint. As said, we are living in exciting times. We are very much at the beginning of the fourth industrial revolution. So what we see right now is that AI is shaping science, and as said, during the next years, you will see agentic AI also taking part in research in a very active way, doing research autonomously. Then questions also arise like, what are the unique tasks we humans can do versus tasks the AI can do? We are not there yet, but I think these are, exciting questions we will deal with in a couple of years. So right now, we are in the situation that AI is already infusing in science in various ways, and we already heard exciting talks in that direction. So here are a couple of examples, like, for instance, experimentation, setup of experiments. So AI can guide us how to do that in an optimal way. Autonomous discovery, learning physical laws, can be from images, for instance, deduce already the underlying physical laws. Then I myself come more from the area of mathematics, so machine reasoning and also automatic proving is on its way. There are already AI systems which, to a certain extent, can take over tasks which mathematicians could do. And I think I need to tell nobody that, education, AI is now a major part of it in every aspect. And I guess every one of you has used AI also in one way or the other to maybe help improve your writing or aspects of that type. So in that sense, I think AI is already part of our scientific infrastructure. And this raises the question, as I said, so can we trust it and can we sustain it? So let me first relate to the first question about can we trust it? So reliability, so we already heard about foundation models. We know they are prone to hallucinate. So we still have a bit problems with safety, which is in particular critical if AI is in some sense a part of our infrastructure. There are still problems with security, so one can hack into those systems. There are problems with responsibility. We sometimes don't understand why decisions are taken. They are not transparent enough. Decisions can be also biased, depending on the training data we have. And so if it's part of our scientific infrastructure, if AI fails, the whole system breaks down. And I think we know this is still, one concern. So there are still a lot of research to be done. I'm coming, as said, more from the foundational side, and so the message, and don't worry, so there are not mathematical formulas here, but what I would like to convey to you is we need to understand in depth, how these systems work. The second part is sustainability. And I'm sure many of you have seen these pictures. In the US, it's very easy. You have a new hyperscaler, you build the nuclear power plants. Next to it, you have enough energy for a moment. Yeah, but that's not possible in Germany. Yeah, we cannot do it. Maybe we also don't want to do that. But I mean, I think in general, the problem is even more severe. So if you look to the picture on the right-hand side, you see here the world energy production, and then you see all these colored lines. This is the energy we just need for communication, and you might know that in a computer today, I mean, most of the energy is actually used for communication and not for the actual compute. And what you see is, I mean, if I change the hardware, I can lower this curve a bit better. And if I'm smart and also use, let's say, mathematics to improve the software aspect, so this is this post-Shannon, I can lower it even further. So this shows, I mean, both hardware, software plays a role, and somehow it needs to also go hand in hand. And so, I mean, one message here is that both of these aspects, which I said I want to talk briefly about, which is reliability and sustainability, one aspect is you need to understand in depth what the problems are, but then we will see that both will actually also link to computing paradigms, which I think is exciting and maybe worth thinking about. Okay, so let's take a mathematical perspective. Maybe I just say verbally, I mean, everything, neural networks and so on, you can basically write down in mathematical formulas, and then you can ask questions like this. Yeah, so you see, I mean, expressivity, how large do I need to build my model, so that I am able to also represent what I want to learn. Maybe it's not even possible. There's the area of learning. So we have this stochastic gradient descent, which I'm sure everybody of you is using. But the question is, so does it converge? Does it converge to the right solution? Can I predict that? And then maybe the holy grail of neural network theory, generalization. I have my training data, everything works nicely. Now I apply it to other types of data. I would like to have error bounds. Performance guarantees, a very technical area, but something which is extremely important to my mind. And then last but not least, explainability. We all know the EU AI Act, it's on its way. It will also, to a certain extent, depending on how you do it, affect research. So certainly then every AI technology has to come with an explainability approach, so that makes explainability even more interesting and important. And I would now like to just very briefly, because I don't have that much time, delve into explainability, show you a little bit, I mean, what the advantage is if you really, I mean, do it from a foundational viewpoint to make this explainability also trustworthy in a certain sense. And then we will come back to, let's say, sustainability and also look at the underlying hardware. So explainability, I'm sure everybody of you have seen these pictures, so I don't need to say much about it. So these pictures show you where the network looked at to reach certain conclusions. We can see when mistakes happen, like on the right-hand side from a dear colleague at TU Berlin. So the network did not look at the horse, it looked at the copyright tag, so the data was biased, and certainly we would like to communicate with an AI like you would with a human. But now, I mean, all these pictures are nice with all the colors, but so if you would like to use explainability to ensure trustworthiness, you have to trust also the explainability approach. So if it just produces nice pictures, that doesn't help you in any way. So therefore, I'm a great advocate of developing explainability approaches which are also based on a foundational viewpoint, where we know exactly what relevance is. We can talk about optimality and maybe also higher level explanations. And I would like to just very briefly show you one approach which we developed where you base it on information theory. And basically, I mean, what you do is you view it as a trade-off between information and distortion. So how do you do that? So information theory is an area where you always have two persons. They are always called Alice and Bob. And Alice has a message. She transmits part of the message to Bob, like you see there. And Bob makes a mistake. And you always have this trade-off between how much is sent and the error which is made. So now you can formulate this whole explainability question in that framework. So Alice and Bob have both the same neural network. Alice has the original image. She transmits parts of the image to Bob, hopefully the relevant part, where the decision is based upon. Bob has to bring it back to image size and apply the neural network to it. And so you have these components, you have how much is sent, the information, and then you have the distortion between the different outputs of the neural network, and you can formulate this as a precise optimization problem. So then you have here the relevance scores, you know exactly what they mean, and you can even then do things like not placing the relevance scores on every pixel, but maybe using a nice decomposition. Most of you work in imaging, maybe you still remember wavelets, so you have nice decompositions of images, and you can place the coefficients, the relevance scores to those coefficients. So let me show you one example, and then I will show you, well, hopefully, the advantage of using this mathematical approach. So I apologize that this example is not from, let's say, from the medical field, but I hope you bear with me. So we worked a lot with telecommunication. So what you see here is a city map. You see the cell phone users, these red dots. You see the white blob, which is a cell tower, and the network computed this black and white background, which indicates how strong the signal is. Yeah? So here it's really bad because there are a lot of buildings obstructing the view. But then you see, this area in this green rectangle, which is also an area of bad reception, although you stand right in front of the cell tower. And so this is the explanation. And in fact, these cell phone users, which you see there, have bad reception. So it makes sense to compute an area of bad reception there. And so what turned out was there was actually a building missing in the city map. So the data was faulty. So, but I would like to show you, just as a final slide for explainability, what the advantage is of, let's say, using mathematics. So here you see, an original image, you see the edges, and then you have two explanations. And for each of the explanations, I also show you the edges. And what you, I guess, would expect is that the explanations do not distort the meaning of the image. So if it would invent certain structures, that would be a problem because you cannot trust the explanation. But what you see is in this shielded X, the edges are a subset of the original image, but not for the other explainability approach. And so now, since we have this mathematical framework, don't go into the details, we can show this rigorously. So we can show that the edge structure of the explanation is always a subset of the edge structure of the original image. And so this is, from my viewpoint, one advantage of really taking this foundational viewpoint. Okay, so far so good concerning reliability, and now we want to dig a bit deeper. We talked only about software so far, so what we neglected is that, certainly compute is absolutely essential. Everybody needs it. But what we do right now is, we use the classical von Neumann architecture. We break everything down to zeros and ones. And I think we have to ask ourselves, is this the best what we can do? And what we did is, there's this beautiful computability theory, so we studied it from that perspective. And what we found out is that certain problems are not computable on digital hardware, so Turing machines. So that doesn't mean it's always wrong, but it means there are some reliability issues which are lurking in the background. And so you can make this mathematically precise. I don't want to show you the details there, but so we showed that for several other problems, and that means, even with perfect training, it could be that there are some systematic errors which happen. And so this shows, a problem with digital hardware. And then you can ask, what do you do? So now we have these GPU clusters, but there are very interesting directions, and one way research is going on the hardware side is more to the analog side, to analog computing. And you can even show that if you use analog machines, things become computable. And there are exciting directions, like, for instance, neuromorphic computing, which is also known to be much more energy efficient. There's biocomputing, where people compute in living neurons. There's also quantum computing. This will not solve the energy problem. It uses a lot of energy, but anyhow, it's a very exciting analog way of computing, and so the hope is somehow to achieve reliability and sustainability by also reconsidering the hardware we compute on. And so let me spend the last minutes talking a little bit about this next generation AI computing, in particular neuromorphic computing, because there you can already buy chips. And so right now, small, let's say, neuromorphic computing clusters are already starting to be built up also here in Munich. So if you compare your brain to a high-performance GPU, I mean, there are in particular two aspects which you immediately notice. First of all, your human brain uses much less energy. I mean, compare 700 watt to 20. And then it has also a very different way of computing. So instead of being digital, it is analog. And so here I usually make this example that if your laptop breaks down, you only have the chance to switch it off and switch it on again sometimes. Maybe everybody has experienced this. Now imagine you need to do that with your human brain. That would be a problem. But the human brain, this analog computing type, is very flexible. And so this goes hand in hand with the von Neumann architecture, which we use these days for computing, versus the neuromorphic architecture, where you have spike trains as input and output, and where on the chip itself you have somehow like a network. And so what neural networks do you run on neuromorphic hardware? Well, I mean, there are so-called spiking neural networks. They are a further development of normal neural networks, where you work through the network layer by layer, but now every neuron acts on its own. And since most of you work in medicine, I'm sure you know that the human brain, the neurons also work in a certain sense autonomously. So here, what you see is, I mean, every neuron acts on its own, so every neuron gets inputs from other neurons, it's building up a potential, and at some point it fires. So time is important in this whole model, and if you store information in time, it doesn't cost additional energy. So that's one aspect why neuromorphic computing is so energy efficient. So there are many models for that, and again, I said I don't want to scare you with mathematics, but let me just show you one slide how you model this. And so this is the definition of a spiking neural network. So you can do, I mean, we have many results also on the theoretical side there, so you can do rigorous mathematics and also ask generalization questions and so on. So we are very fortunate that we also have a large-scale project in this direction. So we have Klimkis now also here. So this comes from both state ministries, from Bavaria and Saxony, and the key goal of this project, which is between LMU TUM and the TU Dresden, is to develop a general framework, also theory-driven, for highly energy-efficient and reliable AI systems for specific application settings, and these will be communication, medicine, and robotics. So my time is almost up, so let me finish with some conclusions. As said, I mean, AI is becoming scientific infrastructure. We need to now ask the same question which we ask for every scientific instrument, which is in particular, can we trust it? Is it sustainable? For reliability, we saw that you can approach it from a, let's say, theoretical side, but also it goes from the computability viewpoint up to the computing, where you compute it on, and with sustainability the same. So let me finish with the sentence, AI must not only accelerate science, it must also deserve to be part of it. Thank you very much.
Thank you very much for the very interesting talk. We have time for some questions. Yes, please, Fabian.
Hey, good.
Hi.
Thanks for a nice presentation. I really like this sort of interpretation, sort of explainable part that you had in the beginning. If I have very big LLMs nowadays, I guess at least part state of the art would be to use sparse autoencoders or so, right? Which sort of is kind of dictionary learning, except for that it has sort of this nonlinear encoding. Mm-hmm. So for dictionary learning, these old things that we used to do, you know, there's some very nice math with respect to spark and uniqueness and all these things.
Yeah.
Do you think there's room for sort of finding or extending some of these results to this nonlinear encoding type of field that is so hot at the moment?
Yeah, thanks for the question. I mean, very, very exciting. There are some results, for instance, I mean, extending this to CNNs. Yeah, so for instance, Miki Elat did something in this direction. But I think from my viewpoint, I mean, they need to be much more in that direction. So, I mean, the hope is really, I mean, these large language models, they are so unstructured, I mean, to also get explainability approaches in that direction, but also transfer, I mean, some of those results to get it on a bit more stable feed. But one let's say also one problem is in a certain sense to model the data which you put in.
We saw so many sort of transformer-based, sort of even foundational model type of talks today and yesterday, and I think many of them would profit from some interpretation.
Exactly, yeah. So the questions I raised, also generalization and so on, I mean, there are also some results getting performance bounds for transformers, and so many people are working on it, but it takes a bit of time. But thanks for the question. That's great.
Thank you. Daniel, please.
Thanks, Gitta. Very nice talk. I was wondering, the explainability part you talked about, it seemed to be in the information theory also strong link to privacy, sort of perhaps whether you sort of can exploit the ideas you just talked about for explainability also for identifying sort of privacy leakage also. I was wondering whether there is some common thread there, or whether that's a completely different way of thinking about explainability.
I mean, so if I understood you correctly, I mean, you're asking if these, let's say, explainability approach that you understand where, let's say, the results come from, that then you also get information on whether it was private or not. I mean, I haven't seen much about this connection so far. Typically, it's, I mean, let's say, separate. I mean, but I think it's definitely worth thinking about, because I believe, I mean, there could be a very interesting direction. So maybe we can talk about it offline. Yeah.
Thank you. I have one quick question, actually, about coming back to trustworthiness. Because it's an interesting concept to think about a little bit, because if we kind of relate reliability with trustworthiness, we might also want to talk about what is trustworthiness, and basically people have different thresholds for trusting a system, right? So what do you think about that? Should we kind of make the human perspective the most important thing there, or are there any concrete ways of measuring trustworthiness?
Yeah, thanks. An excellent question. So, in fact, I mean, reliability, trustworthiness, these are used in very different contexts. I mean, from the EU, there's actually a definition of trustworthiness where you have different categories. One is, let's say, this technical category. One is this, let's say, legal category, and the other is the human aspect. But so here, I mean, for reliability, I mean more the technical aspect. So, I mean, just rigorous, let's say, performance guarantees. So this comes more from the, let's say, systems perspective. But certainly, I mean, the other aspects are similarly important. And I think the question will be also for the future, I mean, how do we specify beforehand neural networks? And maybe we have something like labels, like a refrigerator label. I mean, it's, I don't know. This network is, I don't know, to this extent reliable, it has that energy consumption, and so on and so on, and then you can better compare networks.
Yeah, very interesting. Thank you very much. So please don't leave. I'm asked to, no, not you can leave, Gitta. Thank you very much. We have a small announcement.
Yes. Yes.